Hello. In this part of the lecture, we will work with formulating some of the LP problems. So what we will be given is we'll be given a descriptive statement or of the given system, and then our goal will be to formulate it so that we can apply the LP technique. In these particular cases, we will just focus on the formulation aspect. Let's take a look at a transportation problem. So we are going to look at a company which has manufacturing plants located which are closer to the raw material, water, power, and other production factors. And at the same time, they have warehouses which are located closer to the markets. So the goal will be to minimize the shipping costs of products from the plant to the warehouse. Any plant can send product to any of the warehouse. One of the limitations that we are given is that each warehouse has a capacity limit and they can only accept product until they reach their capacity limit. So our goal is that we should identify how many tons should be sent from each plant to each warehouse in order to achieve the lowest overall shipping cost. Here is the table that we see is given to us. On the left column, we see the warehouse and warehouse A, B, and C. And on the topmost header row, we are told that these are plants 1, 2, 3, 4, 5, and then each cell in the intersection of row and column gives us the cost per ton in cents for shipping products from plant to that warehouse. So, for example, this particular cell is telling us that if we have to ship product from plant 1 to warehouse A, it is 25 cents. Similarly, plant 1 to warehouse B is 40 cents, whereas plant 2 to warehouse A is 33 cents per ton, and plant 2 to warehouse B is 25 cents per ton. Additionally, we are also told that the market requirements, which in our case is the capacity of the warehouses, is 60 tons per day for warehouse A, 160 for B, and 55 tons per day for warehouse C. And the plant capacity of each of the plants is given to be 75 tons, 92 tons, 40 tons, 10 tons, and 68 tons. So, as we have done in the past, our first goal is to identify the decision variables. We are clearly asked that how many tons should be sent from each plant to each warehouse in order to achieve the lowest overall shipping cost. It gives us an indication that our decision variables must answer number of tons from plant to warehouse for combination of plants and warehouses. So we will assume that X1A is the number of tons of products from plant 1 to warehouse A, and then X1B from plant 1 to warehouse B, X1C from plant 1 to warehouse C, and similarly from 2 to A, B, and C, 3 to A, B, and C, 4 to A, B, and C, and 5 to A, B, and C. So we have a total of 3, 6, 9, 12, and 15 decision variables. The next step is finding the constraints. We are told the limits of warehouses. So let's see the constraints based on those. So this equation shows us the constraint for maximum receivable via warehouse. Since the warehouse A may receive shipment from any of the plants 1, 2, 3, 4, or 5, the sum of all the shipments that they receive should be less than equal to the capacity of that warehouse. Similarly, for warehouse B, which will receive from 1, 2, 3, 4, and 5, plant 5, and warehouse C, which will receive from plant 1, 2, 3, 4, and 5, and in this case, warehouse C's limit is 55 tons. Now, the other set of limitations are based on the capacity of the plant. So, From plant 1, the shipment will go out to warehouse A, B, and C. So we have X1A plus X1B plus X1C should be less than equal to the maximum capacity of production of plant 1. Similarly for plant 2, for plant 3, plant 4, and plant 5. Now finally to the objective function, which is minimize. So we are told to minimize the shipping cost, and the Z function will be given by multiplication of the cents per ton by the number of tons from the plant to the warehouse, and then we sum it up for each combination. So this one is from plant 1 to A and the cost of cents per ton of A. This one is plant 2 to A and then cost per ton for shipping in cents from 2 to A, and so on. So that was a fairly simple example, and we went through the 3 steps of identifying the decision variable, defining the constraints, and then finally identifying the objective function. Next, we will look at a problem which is more related to machine shop scheduling. So assume that a certain shop has machine time available which needs to be scheduled most profitably. There are 4 types of tapered fastening pins that need to be manufactured, which are given here. The machine tool time available and profit values are given below. So we are given manufacturing time in hours per lot. So for pin type 1, it takes 10 hours per lot on lathe A, then it has to spend 6 hours per lot on lathe B, and then it has to spend 4.5 hours per lot on grinder G. The profit is $9 per lot. Same way we are given for pin type 2, 6, and 7. The total machine time that is available to us is 50 hours for lathe A, 36 hours for lathe B, and 81 hours for grinder G. We are also told that all available time on grinder G must be used. Since this machine cannot be used for production of any other kind, whereas the lathes may be used for making screws perhaps. So the question is, what program will satisfy these requirements most profitably? And our steps are the same. We identify the decision variables, define the constraints, and the objective function. We are asked to develop most profitable program, and we know that the profit depends on lots of each type of pin. So accordingly, this hints us that the decision variable should be number of lots of each type of pin manufactured. We assume that x1 is the number of lots of type 1 manufactured. Similarly, x2 is for type 2, x6 is for type 6, x7 is for type 7. For constraints, we know that there are constraints in the total time of lathe available, which is lathe A and B, and the grinder G available. For first constraint, we will pick up the constraint of lathe A. So lathe A spends 10 hours per lot on type X1, 5 hours per lot on type X2, 2 hours per lot on type X6, 1 hour per lot on X7, and total time available is less than 50. Similarly, for lathe B, we have 6x1 plus 6x2 plus 2x6 plus 2x7 is less than 36. And for grinder G, we have 4.5x1 plus 18x2 plus 1.5x6 plus 6x7 is equal to 81. So this is something that we should note, because we were told that we want to use all of the time available on the grinder. So we are not saying less than equal to, we are saying equal to. And finally, the objective function, which is to maximize the profit per type. And in this case, which means it is given by maximize Z is equal to 9x1 plus 7x2 plus 2x6 plus 4x7, where 9 is the dollars per pound of x1 type. So 9x1 becomes the profit on type pin 1, and then similarly 7x2 plus 2x6 plus 4x7. The next problem that we look at it is slightly more challenging, and it is a problem of product mix. So let's say a certain manufacturer of screw fastenings found that there was a market for packages of mixed screw sizes. So you could mix different screws in a packet and sell as a mixed packet of screws. His market research data indicated that 4 mixtures of 3 screw types, 1, 2, and 3, properly priced, would be most acceptable to the public. And here is what was found in terms of the mixture. So there are 4 types of mixtures: A, B, C, and D. And the mixture has a specification that in mixture A there should be no less than 40% of type 1 and no more than 20% of type 2 and any quantity of type 3. The selling price is so many cents per pound. Similarly, for mixture B, you have the information that you see on the screen here, that no less than 20% type 1, no more than 40% type 2, and any quantity type 3, and the selling price is 25 cents per pound. Mixture C is no less than 50% type 1, no more than 10% type 2, any quantity type 3, selling price 35 cents per pound. And then type D is literally no restriction on the mixture types. The selling price was 20 cents per pound. For these screws, the plant capacity and manufacturing costs are given below. So you have screw type 1, 2, and 3 which make the mixture. The plant capacity is in pounds per day. So there is 1,000 pounds per day which can be produced of screw type 1, 1,000 for 2, 600 for 3, and manufacturing cost is 50 cents per pound, 30 cents per pound, and 18 cents per pound for screw type 1, 2, and 3 respectively. Question we are asked is, what production shall this manufacturer schedule for the greatest profit, assuming that he can sell all that he manufactures? For decision variables, we are asked to maximize the profit. This hints that the decision variable should be number of lots of mixture A, B, C, and D, because we are given the selling price of mixture. However, the limitations on manufacturing and cost for the ingredients is given in a separate table. This means that we have to consider pounds of screw type per mixture as the decision variable. So I'm going to repeat it. This means that our variable should somehow indicate pounds of screw type per mixture. So accordingly, we will assume that X1A is the number of pounds of type 1 screws in mixture A. X2A is number of pounds of type 2 screws in mixture A. And similarly X3A, 1B, 2B, 3B, and then X1C, X2C, X3C, X1D, X2D, and X3D. For constraints, for example, we are told that in mixture A, there should be no less than 40% of type 1, no more than 20% of type 2, and any quantity of type 3. So the total weight of the mixture A is given by the sum of the screws in that mixture. So if in this case, X1A plus X2A plus X3A will represent that total weight. And so from the first constraint, which is that not less than 40% type 1, we get X1A divided by the total weight of the mixture should be greater than equal to 0.4. Solving this, we get this form, and then further, if we move everything on the left from the right hand side, the constraint shows up as 0.6 X1A minus 0.4 X2A minus 0.4 X3A should be greater than equal to 0. Similarly, if we follow the same steps, we will have a total of 9 constraints. These 9 I am counting by not counting the non-zero. 6 of these constraints are based on the mixture table and 3 are from the manufacturing table. Identifying the 9 is part of your assignment for this week. And let's write down the objective function. The objective function is again maximize Z. So we have 60 cents per pound profit on mixture A. So the weight of mixture A is x1A plus x2A plus x3A multiplied by 60. That will give you the cents in profit from mixture A. Similarly, add on the mixture B and the mixture C and the mixture D, and we should subtract the cost of manufacturing. So the cost of manufacturing is 50 cents per pound, and the total amount of type 1 screw produced is x1A plus x1B plus x1C plus x1D. Similarly, type 2 has cost of 30 cents per pound, type 3 has 18 cents per pound. So this is our maximize function. So finally, if we refine it and solve it further, our maximize z will look something like this. To summarize this lecture, we have looked into how do we convert a problem statement and formulate it to a form so that we can use LP to optimize a given objective function. At the end, we also looked at few examples that only focused on formulation. Thank you.